Today's topic is titled Using Wearable Devices and Deep Learning to Recognize Physical Activities at Work. And it's my pleasure to introduce our guest speaker for today, soon to be Dr. Yishu Yan. Yishu is a key lab member here in our lab at the ergonomics lab. She'll be graduating in December with her PhD in mechanical engineering. She's been in the lab for 5 years, and we're so lucky to have had her here. As I said, she is a PhD candidate, and she conducts research in the UC Human Factors and Ergonomics Lab and the Berkeley Biomechanics Lab. She holds a Bachelor of Science in Engineering Mechanics from Hohai University and an MS in Mechanical Engineering from Johns Hopkins. Her research primarily focuses on quantifying physical exposures, recognizing occupational physical activities using machine learning, and studying human-computer interaction. And with that, it's my pleasure to hand the mic over to Yishu.
Thank you, Alan. Hi, I'm Yishu. Today, I'm going to talk about using wearable device and deep learning methods to recognize occupational physical activities at work. As Alan introduced, I'm a PhD candidate at the Department of Mechanical Engineering. Oops. Work-related musculoskeletal disorders are injuries or pain involving the nerves, tendons, muscles, and supporting structures of the body. Examples include back pain, sprains, strains, tears, and carpal tunnel syndrome. Musculoskeletal disorders have high incidence rates, and also especially for workers engaged in manual material handling activities, such as construction, nursing, and warehousing workers. It have high incidence rate and high cost to employers due to absenteeism, lost productivity, increased healthcare, and workers' compensation cost. It cost over $20 billion in the United States in 2018. So we want to reduce work-related musculoskeletal disorders. The first step is to understand which activities have been performed by the worker daily. After recognized activities performed, we can quantify corresponding exposures. Therefore, those measured exposures can be used as inputs to perform ergonomic risk assessments. This allows us to implement interventions for the task and reevaluate the risk. Ultimately, the goal is to reduce work-related musculoskeletal disorders. There are many ways can be used to quantify exposures. Conventional methods are commonly used in the field. Nowadays, researchers are also exploring video tracking techniques and wearable technologies. Among conventional methods, one of it is self-reports. Workers estimate and self-report the duration, frequency, and the discomfort level they felt when they are working. This image shows an example for workers to indicate the frequency of the discomfort they had in the last month. This method is low cost, it's convenient. However, it highly relies on workers' judgment and can be imprecise and unreliable. For example, having severe low back or neck pain was found to increase the probability of workers reporting higher durations or frequency of the physical load. Also, another conventional method is observational method. The experts observe workplace exposures using surveillance tool. This method is inexpensive. It do not require too much instrumentation, usually just a camera and a predefined template to take handwritten notes. Usually, it's easy to use. It's applicable to a wide range of work situations at a low cost. However, this one also do not have objective measurements, and therefore it can be less validity. The next conventional method is direct measurements. This image shows me using a tape to measure the vertical hand locations when the worker was lifting a heavy load. We also used force gauge to measure the force required, and we performed radio analysis to measure the frequency. This method is more reliable. Only handheld devices are needed. However, as you can see from the image, the person needs to hold this heavy load until I made the measurements about the vertical and horizontal hand locations, which actually distract the task. Thus, this method can be impractical and can be time-consuming. Nowadays, researchers are exploring the usage of video tracking techniques on measuring physical exposures. Photos or videos are recorded in real time and analyzed by dedicated computer software. These techniques are more reliable and is good for postural analysis. However, it is difficult to measure the force required to the weight or the weight handled using video tracking techniques. Also, the performance is not stable. It can be influenced by occlusion and poor lightning conditions. It's hard to ensure that the worker's movements are not obscured when the person are walking. Workers' privacy and confidentiality can also be affected. It was reported that employees feel extra mental stress in a camera-filled environment. The next one is wearable technology. It has been attaching the attention of researchers. Inertial measurement units is one of those wearable technology. It can be used to measure position, velocity, and acceleration of different body segments. Through this image, we can see the person wear a lot of IMU sensors on her body, and in this way, the software created a human model to mimic his movement. The advantage of this method is that it's reliable and it's good for human body motion tracking. They are reliable for measuring joint angles, with previous studies indicating that the IMUs outperform markerless optical systems in accuracy. Also, they have various applications, including the field of ergonomics. However, a disadvantage is that magnetic disturbance can cause errors in IMU measurements, which limits the environments in which they can be used. Wearable technologies have been used in the field of ergonomics already. So, for example, the Active Paw is an electronic logger designed to quantify daily activities in free living conditions. It records the time people spend on lying, sitting, standing, and stepping on a second-by-second basis, which can be used to measure stand and move at work. Another example is wearables placed on the upper traps or the upper arms. Sometimes it can be on the trunk. It can provide real-time notifications for unsafe movements, such as pull lifting techniques, repetitive motions, and sustained awkward postures. So we have already introduced that to measure physical exposures, there are different methods and techniques. The next step is that how can we perform ergonomic risk assessments using those exposures measured? The most commonly used risk assessments tool for lifting is Nash lifting equation. It requires the measurement of the load weight, hand locations in vertical and horizontal at the origin and destination of the lift. Also, the time domain features such as the frequency and the duration. The risk metric of the Nash lifting equation is lifting index. If the lifting index is smaller than 1, this lifting has very low risk. If the lifting index is larger than 3, the risk is very high, and interventions need to be implemented immediately. For other manual material handling activities, including pushing, pulling, and carrying, the most commonly used tool is Liberty Mutual equation. The physical exposures required includes the hand height, the force required, the distance they traveled, and also the frequency they perform those activities. It provides the male or female population percentage capable of performing the task without perceived overexertion. Typically, larger than 90% female is the goal to design a job. If less than 75% female is capable of performing this task, it exposes workers to a much higher risk of injury. The objective of this study is to use wearable technologies to provide a more reliable and valid approach to recognize occupational physical activities, then quantify physical exposures for evaluating risk of musculoskeletal disorders from manual material handling tasks. In the fourth aim of this objective, we are going to focus on recognizing occupational physical activities. The job of a worker decides which occupational physical activities they are performing daily. It includes non-manual material handling activities, such as reaching and some hand exertions. It also includes manual material handling activities, including lifting, carrying, pushing, and pulling. When the workers are performing those manual material handling activities, they are facing different physical exposures, which is associated with work-related musculoskeletal disorders. We will discuss about those exposures later, but for the first aim, we are going to focus on recognizing occupational physical activities. So many studies have already used wearable technologies and deep learning models to recognize human activities. It includes recognizing whole body activities such as standing, sitting, stooping. It also includes recognized daily living activities and sometimes select occupational physical activities. However, there are still some limitations. Recognizing a wider range of occupational physical activities is still challenging due to interclass variability, interclass similarity, the diversity and complexity of activities. Most importantly, most of the current work, they recognize activities when they are performed in isolation. However, it remains challenge on combining several activities in the work task as sub-activities, which limits its application in a real working environment. This one shows my previous study on recognizing occupational physical activities. In the previous study, 8 inertial measurement unit sensors were utilized, and the locations of the sensors can be seen in the left image. The right image shows a person wearing the sensors to do some activities. We applied a deep learning model to predict 15 occupational physical activities when they are performed in isolation, and overall, we reached an overall of 95% accuracy, which is good. However, when we apply the same model to recognize activities performed in simulated work tasks as sub-activities, the accuracy dropped to only 22%. The simulated work task comprised those activities and performed physically. So there are many reasons behind the low accuracy, and I learned a lot from this study. One major reason is that occupational physical activities can be performed concurrently. So looking at this image, do you think the person was lifting or do you think the person was crouching? Actually, I would say both of them is correct. The whole body posture of the person was crouching, and of course, we can see the person was lifting the bag with his arm. So this is why that the lifting has been frequently predicted as crouching, because when we label those frames, it's only labeled as lifting. Especially in simulated work tasks, this happens frequently. Because the activities can be performed at the same time as concurrent activities, it is a big challenge in human activity recognition applications, but it haven't been given enough attention. Thus, in the current study, we separated the prediction of whole body activities and upper body activities. I will start by introducing the overall flow and then explain the details of each single step in the later slides. Occupational physical activities were performed in isolation by 20 participants. The data was used to train and test the deep learning models to recognize whole body and upper body activities. The same group of people also performed simulated work tasks, which comprised all occupational physical activities as sub-activities. The trained model was tested on the simulated work task to recognize which activities have been performed. Multimedia video task analysis had been used as gold standard to manually label which activities in the recorded videos was performed and compared with the model result to calculate the model accuracy of recognizing activities in simulated work task. First, I will talk about experimental data collection. During the whole experimental process, the participants wear all the wearable devices and their video recorded by cameras in different locations. The study included 20 participants aged between 18 to 65 years of age. They do not have any active neck, back, arm, or shoulder pain. The device we are using are 17 wireless IMU sensors from Accents. The left image shows the locations of the 17 IMU sensor. You can see it covers the whole body, including the head, the trunk, and also the limbs. The right image shows a person wearing the sensors and perform the drawing task. The first thing is that the activities was performed in isolation. It includes 7 whole body activities. They are standing, walking, sitting, symmetrical kneeling, asymmetrical kneeling, crouching, and stooping. It also includes 6 upper body activities. They are reaching above, below shoulder non-manual material handling movement, pushing, pulling, carrying, and lifting. The lifting was performed in front of the shelf with 3 vertical heights and 6 locations. The participants perform it from different heights following a sequential manner shown here. In total, 98 lifts should be performed by each participant for every participant. This one shows how the whole body activities was performed. Each of them was performed for at least 1 minute by each participant. To overcome the challenge of diversity of activities, we encouraged participants to vary their posture. As an example, for sitting, we encouraged the people to sit when keeping the feet flat, sit with crossed ankles, and sit with crossed legs. This one shows the upper body activities. Among the 6 upper body activities, carrying, pushing, pulling, and lifting are manual material handling activities. Participants perform these activities with different ways. For carrying and lifting, participants handled boxes with 3 different ways. For pushing and pulling, the required force was divided into heavy and light loads. And 3 simulated work tasks are designed to comprise all those activities as sub-activities. The first one is penny rolls sorting task. The participant sort penny rolls into different baskets, then carry each basket and put them on the shelf. For the carpet laying task, participants put carpets on a cart and then push the cart to desired location and began laying the carpets on the ground. After all carpets were put on the ground, the participant pulled the cart to its original location. The last one is drawing task. The participant draw in 4 different locations with 4 different whole body postures. As mentioned, the 3 tasks comprised all whole body activities and upper body activities. For example, in the left image, the whole body posture here was sitting. The upper body posture here was below shoulder non-manual material handling movement. In the middle image, we can see the person was kneeling with below shoulder non-manual material handling movement. In the right one, the person was standing with reaching above. The whole experimental process takes about 3 hours in total. The next one is data processing. After data were collected, convolutional neural network resonate-18 structures were utilized to recognize activities. Since the whole body activities and upper body activities are separated, one model was used to recognize whole body activities only, and the other one was used to recognize upper body activities only. For data processing, the input data for the model include position, velocity, acceleration, and joint angles measured by using inertial measurement unit sensors. Those input data was labeled with activities. Then the input dataset was converted to form image-like windows. Each window contains 60 rows of the data. Since the sampling rate of IMU was also 60 Hz, it means that each window have 1 second of data. Since each paper have 60 windows for each activity, using whole body activity as an example here, the first 1,200 windows was labeled as standing, the rest of the windows was labeled as other whole body activities. The column number of the windows depends on how many inputs was used to give us the best result. For whole body activities recognition, I only used IMU data collected from the person's lower body. For upper body activities recognition, I only used the data collected from the upper body. Let me explain why we are doing that. Looking at these two images, the upper body activity was both below shoulder non-manual motor handling movements. However, in the left image, the whole body posture of the person was sitting, and in the right image, the whole body posture was kneeling. So we can see that when the person was performing the same upper body activity, she can have totally different whole body posture. I don't want what the person was doing with her lower body to influence the recognition of her upper body movement. So that's why we only use the data collected from the upper body to recognize upper body activities. And that's the same for whole body activity recognition. Processed data of the 20 people was then divided for training, validation, and testing. The cross-entropy loss function was utilized. After training was completed, the best model was selected based on testing data accuracy, which means that how many windows were correctly predicted as the actual activity being performed. The trained model was then applied to recognize activities performed during the simulated work task. To know activities have actually been performed during the task, we utilized multimedia video task analysis as the gold standard. So we analyzed each simulated work task video separately and also manually labeled activities by identifying the terminal breakpoints between different activities. This is compared with the model result to calculate its accuracy. This one shows the prediction accuracy of whole body activities recognition. This is collected on 20 people's data, and as you can see, when those whole body activities was performed in isolation, we got an overall of about 99% accuracy. When this model was applied to recognize activities in the task, the accuracy was 89%. Even though most of the activities still have above 90% accuracy, standing and crouching had relatively lower accuracy, and we will discuss this later. This table shows how the overall accuracy of recognizing whole body activities varied with an increasing number of participants used for train the model. When activities were performed in isolation, the overall accuracy consistently exceeded 98%. However, when activities were performed during simulated work tasks, the accuracy initially dropped as the number of participants increased. Afterward, it plateaued and then slightly increased. This table shows the prediction accuracy of recognizing upper body activities. When activities were performed in isolation, it reached an above 97% accuracy. In simulated work tasks, the overall accuracy of upper body activities was 83%. With lifting and below shoulder non-manual motor handling movements had relatively lower accuracy. Okay, so let's go back to the whole body activity recognition. Crouching and standing had relatively lower accuracy. Sometimes the crouching was mistakenly predicted as asymmetrical kneeling or kneeling. Looking at this image, you can see how the crouching was performed, and the red image shows an example of my participant laying the carpet on the ground with the whole body posture of asymmetrical kneeling. As you could see, for both posture, the knee can be very close to the ground, which adds difficulty for the model to have correct predictions of crouching. For standing, it was sometimes mistakenly predicted as walking or crouching. The reason is that when performing the task, the person do not just stand straight. They can move their body a little bit. They can shake their legs. They can move their foot. Since we only make prediction for each single second, for 1 second of this period, the standing could be looks like walking, and that's why sometimes it's mistakenly predicted. This one shows the result of predicting upper body activities. The way lifting have been performed in isolation, which was used to train the model, was different compared with how it was performed in the task, which was used to test the model. When it was performed in isolation, they lift the boxes in front of the shelf. However, in the task, they either lift the basket with penny rolls inside or they lift the copies. So they actually lifted different objects. And also, when they're performing the copy laying task, sometimes they use one hand to hold one set of the copies, and then they use the other side to catch the other set of the copies. So the movement is not that consistent compared with when they are lifting the box. So the variety and diversity of lifting. For example, the one-handed lifting, lifting from different locations, lifting while stooping or crouching makes lifting hard to predict. Another one with relatively lower accuracy was below shoulder non-manual material handling activity. This one includes reaching below shoulder level, as well as other non-manual material handling movements, such as walking or standing with limited arm movements, so this one have a large diversity of how it can be performed. As a discussion, one challenge of the study was the variance of how activities were performed during the simulated work task compared to being performed in isolation. As we just discussed, there are so many ways people can use to lift an object. Although participants lifted many times when the activities were performed in isolation, it was insufficient to cover the full range of approaches they actually used when completing the task. Another limitation is the transition times, when the participant changed from one posture to another. For example, when they kneel down to lay the copies on the ground, they changed from standing to kneeling. And those transition time was difficult to assign even when we are labeling by looking at the video. And also it was difficult for the model to recognize. You may notice that the upper body activities had lower prediction accuracy compared with whole body activities. The reason is that the upper body activities sometimes engaged in manual material handling, making it more difficult to define the starting and ending of these activities. Even though we have definition about how to label a pushing or pulling, it's pretty hard to strictly adhere to those definitions. For example, the ending of pushing was defined as the hands of the cart. However, for many cases, we saw that one hand was still on the cart with the other hand already left the cart for a couple of seconds. And in this way, it's hard to decide from the video whether the person was still applying the force or not. So that's why this is hard to predict and hard to label. Overall, these accuracies indicate that this approach could be used to reflect the percent time spent in each activities, as required in a physical demand analysis, even though in simulated work task. So we have already talked about the first aim, which is recognizing occupational physical activities. Now let's move to the second aim, which is quantify physical exposures for evaluating risk of musculoskeletal disorders from manual material handling tasks. As we mentioned, when they're performing manual material handling activities, including lifting, carrying, pushing, and pulling, they are facing different physical exposures. The most important exposure is the awkward posture and the high force. The increasing distance from the weight to the worker's body, the flexation and the heavy loads will increase the muscle force, span compression force, and span shear force. Other physical exposures include the long duration and high frequencies of performing these activities. Those exposures lead to increasing risk of work-related musculoskeletal disorders. And this is what we are going to focus for the second aim. As introduced in the aim1, the convolutional neural network model predicts which activity have been performed during simulated work task, using penny rolls sorting task as an example. The person sort penny rolls into a different basket, which is below shoulder non-manual material handling movements. And then the person lift the basket and then carry the basket to the shelf. During the period when it was predicted as lifting, this is a screenshot taken from this period, and we can count it as one lift. So this way, it allows us to count the number of lifts performed by each participant while completing each task, representing the frequency feature required by using the Nash lifting equation. Multimedia video task analysis was used as the gold standard again to analyze videos, label each lift, and identify frames corresponding to the origin and destination of each lift. We also used the CNN model to recognize the number of lifts, and we developed a velocity-based method to recognize the frames of origin and destination based on the variable device output, which is the IMU data. If the frames between these two methods was within plus minus 30 frames, which is corresponding to half a second, we take this recognition as a correct recognition of the origin or destination frame. So the velocity-based method have been used to identify the origin and destination frame of the lift. The next step is to use the position features from the variable device to quantify the horizontal and vertical hand locations. In this way, we can also obtain information regarding the distance factor, vertical factor, and horizontal factor for using Nash lifting equation. The only thing cannot be able to obtain by using variable device and deep learning methods would be the coupling factor at this moment. As for the results, during simulated work task, the CNN model correctly identified the periods of lift for 77 percentile of the time. Based on full participants' data, for the frequency, 98 percentile of the lifts out of 55 lifts in total was correctly identified during the work task. For origin and destination frames, about 55 percentile of the origin or destination frames was identified accurately, which is within plus minus 30 frames. For hand locations, previous pilot data have already shown that an error of less than 6 centimeters and 2 centimeters in measuring vertical and horizontal hand locations, respectively. And this error do not have large influence on the result of ILE risk assessment. There are still some limitations about this method. Although this method indicates the ability to identify at least half of the origin and destination frames, it's not able to identify when lifting was immediately followed by carrying. Such as this one, the person lifted the basket and carried it to the shelf. If that's the case, it cannot recognize the endpoint of this lift, and this one counts for 21 percentile of incorrect recognition. And also, this method is not feasible in cases where only one hand was utilized for a portion of the lift. The red image may not be clear enough, but you could see that the person used the right hand to lift the copies, and later she used the left hand to catch the other set of the copies. The other thing we want to quantify is the load lifted, because it's required to using the revised Nash lifting equation, and also it's required for liberty mutual equations. Because of this, we didn't only use the IMUs, we also utilized pressure inserts during the whole experimental process. The pressure insert we used are shown here. It has 16 wireless pressure sensors in each foot. The locations of the pressure sensors can be seen in the red image. During experimental process, participants wear both the IMU sensors and pressure insert sensors. For our pilot study, when those activities were performed in isolation, pushing and pulling, as well as carrying, had relatively higher accuracy on recognizing the weight. However, when we try to recognize the weight performed during lifting activities, the overall accuracy was only 57 percentile. There are many reasons behind this lower accuracy. This is because for pushing and pulling as well as carrying, as we can imagine, the person was always standing or walking. However, lifting was much more different. When the person was lifting to some locations above their head or in front of them, they're standing. However, when they're lifting to the ground or someplace lower, they're using squatting or they're using crouching. In this way, the center of the mass could be either at the center of the foot, it could be at the heel, it could be at the toe. In this way, the force distribution varied a lot, which adds difficulty on recognizing the weight handled during the lifting. And also, as you can see, the weight we used here is 2 kg, 5 kg, and 7 kg. The differences between those weights are relatively small for us to recognize the weight handled. As a discussion, so in the fourth aim, we already mentioned that wearable technologies can be used to recognize occupational physical activities. As we could say, for both whole body activities and upper body activities recognition, the model reached high accuracy, which is about 97 percentile when those activities were performed in isolation. Although the activities recognition accuracy decreased in simulated work tasks, which is still larger than 80 percentile, the results indicate that this method could accurately predict and quantify activities performed during a task. Also, we have used wearable technologies to try to quantify physical exposures and inputs required for well-validated risk assessment tools, such as reverse non-lifting equation. The inertial measurement units had a high accuracy on recognizing the frequency of lifts. It recognized 89 percentiles of the lift in the task. More than half of the origin or destination frames of the lifts was accurately identified, which allows for quantification of corresponding hand locations with small errors. However, we also noticed that the pressure insoles showed lower accuracy in recognizing the weight of the load lifted, which is a limitation of the current study. As a conclusion, most importantly, this study demonstrates that the potential for using this approach in real-world environments where multiple occupational physical activities were performed concurrently within a task for ergonomic risk assessments. We also have some next steps that we're going to conduct. The first thing is that even so far, we only analyzed the data for activity recognition for 20 participants. We have already collected data on 30 participants. So I will finish the analysis on 30 participants' data. And also, we will try to investigate other approaches for load assessment. And the last step is that we want to expand to composite lifting index estimates. The reason is that traditionally, when the person performing lifting for an hour, there are usually hundreds of lifts. It's almost infeasible for the ergonomics to do the lifting index for every single lift due to the time limitation, and also we just cannot perform the direct measurements on so many lifts. So by using this methodology, we could quantify those lifts automatically, and also we could quantify some of the origin and destination and measure the corresponding hand locations, which makes it possible to provide a more valuable input into the composite lifting index. That's why the next step also includes expand it to composite lifting index estimates. So thank you for your listening, and I also want to thank to my labs, and also feel free to ask if you have any questions. Thank you.
Thanks a lot, Yishu. That was really interesting, and I think it really highlights the challenges involved in your work. If anyone has any questions for Yishu, please do enter them into the Q&A box. and we'll do our best to get them over to Yishu here. I do have one for you, Yishu. It's actually a three-part question, but instead of stacking them together, I'll give them to you one at a time. The first part of the question is, have you considered using this study technique in the real world situation, such as a warehouse or distribution facility?
Yes, I think that would be our next step because we want to develop this method for the real world setting. Even though so far those studies were conducted in the laboratory-based setting, we still try to mimic the real world task. So I think in the next step, we will try to apply this technology to in the field data and see how it works with the in the field data. We already got some data from the gender study, so hopefully I will be able to analyze those data and see how it works.
That's great. The second part of the question is, would the results vary based on time on the job and improve with training and education?
You mean spend on the you mean the time spent on the job for each single worker? Is that what you mean? Could you please explain that?
I think the question is arguably ambiguous. I will just the questioner can restate that for us. That'd be fine. Do you think indoor or outdoor environmental factors could affect the test results?
It could be. The reason is that we use the technology of IMU sensors, and we do know that IMU drift is common in some environment, such as some magnetic environment. So in some indoor with a lot of metals or magnetic stuff surrounding, it can have an influence on the result. So it really depends on where we utilize this technology, and that's why we mentioned in the limitation set that it may limit the environments it can be applied.
What experience have you had with the sensors interfering with normal work, or any complaints of discomfort while wearing these sensor systems?
Actually, not from my participants, because for the annual sensors, as we could see, they are usually lightweight and they have a smaller size. When it was put on people's body, it's not that uncomfortable. And for the pressure insoles, many of my participants, they even forgot that they have pressure insole when we finish data collection, and I have to remind them to return this insole back to me. So I would say they are not that uncomfortable. Also, another next step is that we will try to minimize the number of inertial measurement unit sensors required to reach also high accuracy. And in this way, hopefully we can reduce the sensors put on people's body to reduce the influence on the workers.
Thank you. Two-part question. How much does body size influence the prediction, the predictive quality, and what was the distribution in terms of body size among the participants in your study? Did you record that?
Yes, I did read. I didn't read. Oh, I do have the head information. I have not looked at the standard distribution of my participants' height yet, but for my study, I do have male and female from different age. So I trained those data together. So I would assume that it will not have a big influence. But this is a very good point. I will look at the standard distribution and average of my participants' height.
Thank you. What additional steps need to happen to assess good posture versus bad posture?
I think we can use those well-validated ergonomic risk assessment tools. For example, the now lifting equation, it gives us information about if this is a good lift or if this is a high-risk lift. And also there are a lot of posture-based assessment tools which can use the joint angles measured from the wearable device to identify if this is a good posture or not a good posture. For example, when people are doing lifting, we do encourage people to lift when they are crouching rather than lifting when they are stooping. So that some information can be given by looking at the joint angle of people's trunk.
All right, thank you. I've got one more question in the queue. If you have any questions for Yishu, we do have a few more minutes. Feel free to throw them out there. What do you recommend to use instead of IMUs to prevent workers' interruption in their workplaces? So maybe like alternatives to that, to tracking, video tracking, for example. Anything else?
Video tracking had been used in many cases, and also there are already a lot of studies using video tracking to quantify activities. And also there are already many studies using video tracking to track people's body movement, which can also be used to quantify the posture. And this, I think video tracking is a good alternative, even though they also have some limitations, but they have very good precision and also they are very efficient.
Excellent. Well, thank you, Yishu. I think we'll move on to closing. Oh, okay. Hi, David. Thank you for that. Do you see wearable devices getting smaller and easier to use, such as the shoe insert shown earlier, perhaps other textile sensors in the future?
Is the question for
The question is really about, do you envision wearable devices becoming smaller in size, the form factor being integrated into clothing, for example, or
yes.
um,
Yeah, I do think so because the MEMS technology is developing so fast. There are already a lot of MEMS IMU, which also a lot of commercial IMU, there are MEMS IMU, which gets smaller and smaller. And also the price is not as expensive as it could be before. So I do think that with the development of the technologies, those IMUs will be smaller with higher precisions. And there are already a lot of efforts on limiting the influence of IMU drift issue. So by all those efforts, I believe that the IMU will be smaller, lighter, and also probably in the future embedded into people's clothes. And also it may have more higher accuracy and we don't have to worry about the drift as much as we do now. So I really hope that can happen.
okay, thank you. The next question. This is an interesting question about sort of preparing your volunteers for your model in isolation. Did you consider any psychological factors that may have affected your learning, your model results, essentially? Any kind of increased pressure for your participants? Do you think you recorded sort of normal activity for your training?
We really try to record the normal activities. For example, when those activities were performed in isolation, we do tell them that what is activity because sometimes they feel confused about what is sleeping, what is crouching. But we also encourage them to do the normal way they would do at home. And also during the simulated work task, we tell the person how they would complete the task, but we do not give them demonstration about how each single step should be performed. So we let them to have enough flexibility to do those activities on their own source. So that's why you can say in some of the data, when people are lifting the copies, they do not use both hands, they use one hand and the other hand later. This is because we didn't tell them you have to use two hands. So we really want them to do whatever they would feel comfortable with when they're doing on their own. But of course, that is a laboratory-based study, so it may have some influence regarding that, but we think we really try to mitigate this influence.
That makes a lot of sense. Thank you. And then another question is, do you think this technology could be integrated into personal protective equipment for construction workers?
Yes, because IMU have also been used for fall detection and some other personal detecting techniques. So I think that will be, I think already some studies have already been doing that.
Excellent. All right. Well, thanks again, Ishu. That was fantastic. I think we'll move on to our closing remarks here. Everyone can learn more and register for our upcoming events at coeh.berkeley.edu. You can also subscribe to our YouTube channel, where you'll find recordings of previous webinars and other events. As a reminder, if you logged in today with your registration email, you'll get a link to an evaluation form that will qualify you for a 1 hour certificate of completion with one continuing education contact hour. If you have any questions for us in general about anything you see on our YouTube channel, you can reach out to us at COEH Northern California you can drop us a line at coehce@berkeley.edu. That's coehce@berkeley.edu, and someone will get right back to you. Thank you again to our presenter today, and we'll see y'all at the next one. Yishu, thanks so much. That was an
Thank you.
excellent presentation.
Thanks,
Fascinating work.
everyone. Thank you.
Bye all.